When Marie Curie began working on radioactivity in addition to her scientific research, she initially faced challenging moments. This was because radioactivity was an incredibly random process. Up until that time, all known physical processes had a specific cause and a definite result, but it was natural for a certain atom to decay, and whether it would produce radiation was unpredictable. Randomness does not tell you when an atom will decay or not decay, because it says it's impossible to predict decay. However, this randomness can also be used to make incredibly precise predictions. It is one of our most reliable theories. So how does this happen? How can an unpredictable universe be so reliable? First of all, quantum mechanics is now available. The model we know as electrodynamics works almost perfectly when evaluated with test capability. The limits of this model are not theoretical. Our experiments determine them one by one. Let's explain it like this: the G factor of an electron. This value, which explains the relationship between the spin of an electron and its magnetic properties, can be measured with an accuracy of 1 in a trillion. This is akin to estimating the distance between the Snake Tower and the Statue of Liberty in America to within 1/10 of a hair's breadth. We have a very reliable theory. So we need to understand randomness well. The randomness of a quantum system has very predictable shapes and energy levels. But when you try to measure the position of an electron in this orbit, you will see that it is random and unpredictable. In fact, one of the greatest triumphs of quantum mechanics was proving Albert Einstein wrong. We saw that according to quantum mechanics, God throws dice. Everything in the universe exists in multiple states. But when you make a measurement, make an observation, it immediately comes to a certain state. Putting aside what observation is and what measurement does, the result of a known measurement, that is, where something will be found, is incredibly random and unpredictable. It doesn't seem possible to fall at any point. So it seems random, but it's actually not random. Unfortunately, it's impossible to say this. So yes, a truly random universe, a quantum universe. For example, when a light beam or a photon passes through a beam, splitter or a splitter, it splits into two beams along with its energy. What we call a wave explains this. It's easy. Some of the energy of the wave is transferred directly. Some is splitter. Even if Dahan-Shaker reduces energy in quantum theory incredibly and adjusts it to send one photon each time, you still continue to define light and everything else as a wave. So how do you mathematically explain the reflection or transmission of a wave? Strange things begin to happen. Light is split into two and moves in two different directions. It is impossible for you to understand that one of the detectors is giving you a random warning. So yes, there is an irreducible randomness in the measurements of physical systems of quantum. It is not possible to make a correct prediction as in the previous example and countless other examples. In fact, there is such a car, and this car is at a crossroads. You are trying to remotely predict which way this car will choose. Normally, although this seems completely random, the situation is a little different in quantum mechanics. A beam of light or a photon, when passing through a beam splitter, as in the previous example, passes through both paths at the same time. It can be thought of in this way, so when you go to the end of the separated paths to determine which path the car has chosen, you can observe that the car has actually gone in both directions at the same time. Doesn't it look strange? This is impossible, and the problem arises here. Because in traditional physics, from Newton's laws of motion to Maxwell's equations, everything is based on the idea that we live in a deterministic universe. So if we know all the initial conditions of a system, it is assumed that we can predict the future state of that system exactly. But quantum mechanics fundamentally shakes this understanding. A fundamental feature of quantum mechanics is Heisenberg's uncertainty principle. This principle determines the position and momentum of a particle. It says it's not possible to make a measurement with a certain precision at the same time. Imagine not knowing exactly where a ball is, how fast it moves in a football match. In the quantum world, it is a little different. Although it seems completely random, it is not deterministic. Even experiments done with the same initial conditions in the macro universe can give different results. Probabilities govern the universe we live in, and quantum mechanics achieves extraordinary success in predicting these probabilities. Of these probabilities, we can use the dice-throwing analogy. Here again, yes, you cannot know for sure which number will come up. Each face of the die has a chance of coming up. However, we can calculate these probabilities. Quantum mechanics does the same for much more complex systems. It calculates probability waves. As we mentioned, the possible positions of an electron around an atom are actually shown as a probability cloud. Although it seems completely random where you will find an electron at a certain moment, the probability cloud shows where the electron will be or where the probability of being is not. This is actually similar to weather forecasting. Although we cannot predict which street will rain, knowing the probability of rain helps us decide whether to take an umbrella or not. So why is quantum mechanics considered the most accurate theory in history, despite not giving definite results? We need to keep this information in mind to understand this. The real world seems very predictable to use. It is not the case, because in the real world, in the macro universe, even experiments done with the same initial conditions can give different results. Probabilities govern the universe we live in, and quantum mechanics achieves extraordinary success in predicting these probabilities. This random universe for random theory, classical theories can be derived from an experiment. Expects only one result, but quantum mechanics gives the probabilities of all possible results and thus provides a much more accurate picture of how the real world works. In fact, think of a football match. Even though we cannot predict the exact outcome of the match, we can have an idea of which team is more likely to win. Quantum mechanics gives us the betting odds on the possible outcomes of this complex match in the universe. Can we say that the subject is closed? Actually, we can say that by saying this, but someone's spirit is still wandering among us. He may have died, but he is still somewhere here, continuing to confuse someone's mind. Who is this? You know very well who he is. Of course, dear Albert, God was throwing dice and Einstein lost. There were no hidden variables. Although they are in the minority, some physicists are still looking for ways to vindicate Einstein. Of course, the issue is not Einstein, but the search for these hidden variables is not over yet. This includes scientists like Sheldon Goldstein dead left and Nino Zanghi, who work on these models, have seen that quantum mechanics explains both the relative particle processes quite consistently and can make exact predictions while doing so. Although they say there is still a long way to go, in summary, they say this. They say that quantum mechanics may not be as random as it is thought to be. It may seem so. So we are witnessing a revival of the legendary discussions that started at the 1927 Solvay Conference. While quantum mechanics builds the modern world with the randomness it contains, these scientists, who are trying to find the weak points of this very useful theory, are they going to offer us a new story? We don't know, but we love this story in every way. What do you think? Will we find a hidden variable? Will Einstein, who was able to reach the theory of everything, smile at us from the dusty pages of history? What do you think? Until we meet again, as always, good luck with love.